Hello everyone, I'm Haoning Wu from Shanghai Jiaotong University. I'm delighted to have the opportunity today to present our work accepted by ICCV2025, MRGen, a segmentation data engine designed for underrepresented MRI modalities. First, our motivation stems from two observations. In medical imaging, there are pronounced differences across modalities, not only among CT, X-ray, ultrasound, and MRI, which involve distinct imaging principles and acquisition devices, but also within MRI itself, where different modalities can exhibit substantial variation in appearance. These discrepancies, compounded by the inherent scarcity of medical data, constrain the generalization capability of downstream models. For example, consider the T1 and T2 SBIR images on the left. Although they depict the same abdominal MRI and share very similar segmentation masks, an NNU-net trained on T1 data almost completely fails when applied to T2 SBIR. To address this issue, we investigate leveraging data generated by generative models to enhance downstream task performance. Fortunately, this approach proves effective and establishes a new application paradigm for generative modeling in the medical field. In prior work, several excellent papers have explored the use of generative models in medical imaging. However, they are often confined to augmenting modalities that already have sufficient annotations, as illustrated in subfigure A. In contrast, we focus on underrepresented modalities, those with very limited manual annotations, or even no annotations at all due to rarity or high labeling costs. Image-to-image translation offers a potential solution for this setting, but it is inherently constrained. It typically supports translation only between specific modality pairs and still relies on existing annotations. Therefore, MRGen adopts a new paradigm. We pre-train on large-scale, multimodality data comprising both annotated and unannotated images. After pre-training, MRGen can directly generate MRI images of specific modalities for downstream training in a controllable manner, conditioned on a textual description of the target modality and a constructed mask condition. To train such a controllable data generation engine, we begin from the data side by constructing a large-scale radiology image text dataset, MRGen-DB, primarily curated from Radiopedia and existing segmentation datasets. It features rich modality labels, modality attribute descriptions, anatomical region descriptions, and a subset with organ-level segmentation masks. As shown on the right, MRGen-DB focuses on abdominal MRI and covers multiple organs, including the pancreas, prostate, liver, kidneys, and spleen, across diverse modalities. For data curation and processing, we employ knowledge-enhanced strategies to improve data quality. Specifically, we use Biome CLIP to map each radiology image to predefined anatomical regions. This is important because the abdominal cavity spans a wide area, within which imaging characteristics vary substantially across subregions. This mapping helps enrich and disambiguate image annotations. In addition, we leverage GPT-4o to normalize modality descriptions into a fixed template, emphasizing the relative signal intensity and brightness contrast of key constituents such as water, fat, and muscle. This design choice addresses a practical limitation. Even text encoders trained on medical corpora struggle to distinguish simple inputs like T1 versus T2, and they cannot finely control subtle intermodality differences and correlations. Our model design is intentionally straightforward, largely adopting the architectures of stable diffusion and control net, while introducing several training strategies to adapt the system to the medical domain. First, given that medical images typically have high resolution and require clear textual detail, we pre-train a VAE to map high-resolution radiology images into a low-dimensional latent space. This pre-training uses a large corpus of Radiopedia MRI images from MRGen-DB. Next, within this latent space, we train a text-guided generative model using image-text pairs from Radiopedia MRI with a diffusion loss. The resulting model, trained on large-scale paired data, serves as a foundation model for Mr. Image synthesis. Finally, we jointly train a mask controller using a mixture of data with and without mask annotations, enabling MRGen to perform controllable generation conditioned on a provided mask. Next, we introduce our experimental setting. Recognizing that acquiring annotations for truly underrepresented modalities in real-world scenarios is labor and time-intensive, we simulate this clinical context by constructing a series of dataset pairs. Specifically, each pair consists of a source domain and a target domain. The source domain provides images, corresponding textual descriptions, and mask annotations, while the target domain lacks mask annotations to mimic underrepresented modalities. In total, we construct 10 such dataset pairs. Within each pair, we jointly use data from both the source and target domains to train MRGen's controllable generation capability. We then combine the source domain masks with the target domain textual descriptions to controllably synthesize target domain data. These generated samples are subsequently passed through the data selection pipeline shown at the bottom right to curate high-quality generations. Finally, we assess both the quality of the generated data and the segmentation performance of downstream models, NNUNet and UMamba, trained on this data, thereby providing direct and indirect evidence of MRGen's effectiveness. Regarding the experimental evaluation, we begin with quantitative results. For generation quality, we report FID to measure both the fidelity of synthesized images and their distributional discrepancy from the ground truth. The inherently high FID between the source and target domains underscores the substantial cross-modality differences. MRGen significantly outperforms data augmentation methods such as dual norm, as well as image translation approaches like CycleGAN and UNSB. We also evaluate downstream segmentation performance using dice score on models trained with the generated data, providing an indirect measure of MRGen's data quality. Models trained solely on the source domain almost completely fail on the target domain, and both augmentation-based and translation-based baselines yield only limited improvements. In contrast, NNUNet and UMamba trained on MRGen-generated data consistently achieve substantial gains across all dataset pairs, attaining state-of-the-art performance in nearly every pair. We also provide qualitative comparisons for both generation and downstream segmentation. First, one can clearly observe pronounced differences between the source and target domain data, which pose challenges for cross-modality segmentation. In terms of generation, MRGen's synthesized target domain images adhere to the input mask condition while largely matching the target domain's imaging characteristics, an essential prerequisite for training downstream segmentation models with robust performance. For the segmentation task, NNUNet trained on MRGen-generated data performs well in cross-modality settings and substantially outperforms other baseline methods. In the additional results, we present further quantitative evidence to demonstrate MRGen's effectiveness and comprehensive applicability. First, we conduct extended comparisons with additional methods. These include approaches that rely on oracle inputs, such as SAM2, which requires a bounding box or a low-resolution mask of the target as a prompt and thus is not strictly zero-shot, as well as segmentation models trained on large-scale, multimodality data, including UniverseEgg and Total Segmentator, few-shot baselines like NNUNet few-shot, and NNUNet trained directly on annotated target domain data. Entries shaded in gray indicate comparisons that are not entirely fair. Even so, MRGen outperforms existing baselines, including MASI, and achieves performance comparable to methods that leverage oracle inputs. We also include ablations on the VAE and text-guided generation. Compared with a vanilla stable diffusion setup, our VAE employs a higher capacity latent space, which markedly improves synthesis quality for medical imaging. Moreover, clip text similarity computed with Biome CLIP corroborates the effectiveness of our knowledge-enhanced text conditioning. Beyond constructing MRI dataset pairs, we build CT to MRI pairs to further validate MRGen's scalability and broad applicability. We additionally show that incorporating unlabeled target domain images during training and applying a SAM2-based filtering strategy both yield performance gains. Finally, beyond the more challenging cross-modality setting aimed at underrepresented modalities, MRGen is also effective for conventional in-domain generation. Specifically, segmentation models trained solely on MRGen-generated data achieve performance comparable to their fully supervised counterparts, while MRGen also facilitates the generalization of NNUNet to other modalities. Finally, we conclude with a summary of our contributions. We propose a new application paradigm for generative models, using them to synthesize MRI for annotation-scarce modalities, thereby facilitating the training of downstream segmentation models targeting underrepresented modalities. We curate and build MRGen-DB, a large-scale radiology image text dataset with detailed modality labels, modality attributes, anatomical regions, and organ information, with a subset also providing mask annotations. Building on this, we develop MRGen, a diffusion-based controllable engine for generating segmentation data. MRGen produces high-quality MR images and enhances zero-shot segmentation performance on modalities lacking annotations, demonstrating potential clinical value. The QR codes below link to the MRGen project page, the paper, and my personal page. I welcome further communication and discussion. That concludes my presentation. Thank you for your attention. I welcome any questions and would be happy to discuss further.